Welcome student to the next lecture of halogen derivative. Today we'll first understand some basics of reaction mechanism. In 11th standard we have studied a chapter that is structure of atom, and that we have studied that electrons resides in an orbital. Which orbital? If you remember, we have different types of orbital. It is S, P, D, F, and these electrons are found to be present in these orbital, right? Atom, you remember, atoms have shells have subshells have orbitals, and in orbitals electron resides. Now, so electron resides in this orbital S, P, D, F. We're also studying one chapter, that is molecular orbital theory. We have studied one part in that. Molecular orbital theory, in that we have studied that there's a presence of something called as bonding molecular orbital. And in the same chapter and the same subtopic, we also studied something called as anti-bonding molecular orbital. You remember? Okay. Now, we start from there. Now we have to understand, see, we are studying basics of reaction mechanism, and obviously we're going to study about SN2 and SN1. Today we'll be studying SN2, but before understanding what is SN2, we need to understand what is the basic part of that. What is how the electron resides in atomic orbital, how in a chemical reaction atomic orbitals and bonding molecular orbitals and anti-bonding molecular orbitals are used. We have to understand that. So let's see that first. I'm writing one thing. See what I'm writing. Every bonding molecular orbital is accompanied with anti-bonding molecular orbital, right? Every bonding orbital is accompanied with anti-bonding molecular orbital. That is the first thing. Secondly, where this anti-bonding molecular orbital is present, this anti-bonding molecular orbital is placed opposite to bonding molecular orbital. I make you understand. Now student, suppose I say this is one hybrid orbital, right? Okay, so let's see, this is of carbon or whatever. Okay, so and this is going to obviously form with something else, right? So because this is going to form a bond, I will say this is bonding molecular orbital. Okay, and we normally in a books we studied this. There's a bonding molecular orbital which form a bond. If I say there's a bond between carbon and carbon, that means carbon has bonding orbital. This carbon will also have bonding orbital, right? So this bonding orbital is going to overlap with this, and I will say the bond is formed, right? But one thing more we have to understand is that if this is a bonding orbital, here there will be presence of anti-bonding molecular orbital. Similarly, if there is a bonding molecular orbital over here, then there will be presence of anti-bonding molecular orbital. So this will be anti-bonding molecular orbital. Is this clear, students? Again, I'm saying what we have to understand, there's something called bonding molecular orbital, there's something called anti-bonding molecular orbital, right? These two, when I say if there's a presence of bonding orbital, obviously there will be presence of anti-bonding molecular orbital for sure. And where they are placed, it is just placed opposite. This anti-bonding molecular orbital is placed opposite to bonding molecular orbital, right? Opposite to bonding molecular orbital. Okay, We understood this? Clear? Okay. Now, moving to the next point. Generally, anti-bonding molecular orbital are empty. Generally, they are empty. Okay, now what does it mean? Understand. Suppose I say there's a bond between carbon and chlorine, right? Okay, now how I will show in the terms of orbital. Suppose this is carbon, this is a bonding orbital of carbon, right? Here I write chlorine, and suppose this is a orbital of chlorine, right? They have a form a bond, right? So bond is formed between carbon and chlorine. So electron will present in this, right? Suppose I say this is electron of carbon and this is electron of chlorine. You understood this? Okay, and the bonding is formed between them, right? Now here there will be presence of anti-bonding molecular orbital for carbon. Here obviously here also we have anti-bonding orbital of chlorine, right? But what we know is when a bond is formed, how many electrons is present? 2 electrons. You understood this? There's a presence of 2 electrons. So if both the electron is present, suppose here, right, in this bond, right, then this will be empty. This will remain empty. Generally, bonding orbital contain electron and anti-bonding orbital do not contain electron. They are normally empty. So what is the use of that? These empty anti-bonding orbital are used when the reaction takes place, and this is the most important part, right? We have to understand this. We need to understand this. Whenever the reaction takes place, these anti-bonding molecular orbital plays a very, very, very important role, right? How we'll understand further when I start with the mechanism, right? But you have to understand this point. Anti-bonding molecular orbital generally are empty. Okay, and one more point, student. Both bonding molecular orbital and anti-bonding orbital can hold maximum of 2 electrons, right? Both bonding and anti-bonding orbital can maximum hold of 2 electrons. Let's understand. Suppose this is carbon, this one is chlorine, right? And 1 electron is of carbon. Okay, and we understand one thing more, student. In a chapter structure of atom, we have seen that electron has dual nature, right? Electron behave as a particle, electron behave as a wave. During the reaction mechanism, actually we study on the basis of wave mechanism. That is, we assume electron as a wave. Understand? If we start understanding electron as a wave, our organic chemistry will literally become very, very simple, right? So you have to understand that electron in a wave form rather than the electron in a particle form. Okay, so henceforth I will try to explain the things in a wave form. Okay, for that I need to make some explanation, right, which will give you the relevance how that waveform will be used in this mechanism, right? But for time being, let's understand. When I say electron as a wave, so that means electron will be in the waveform present here in chlorine as well as carbon, right? Okay, so if I say how many, see, actually carbon gives one electron and chlorine gives one electron, right? For form a bond, carbon will give one electron and chlorine will give one electron, right? So I will say there is a presence of two electrons. But if I assume they are in the form of waves, so these electron, right, will be like this. Okay, if you think about in the terms of particle also, if I say this one electron is of carbon and this one electron of chlorine, how many electron is present in the orbital of carbon? You will say 2, because you consider this also and this also, right? If I ask you how many electron is present in chlorine orbital, again you're going to say 2, right? But this 2 plus 2 will not going to be 4, right? Because 2 electron here, 2 electron here. In total, if I ask you how many electron, you will say 2, right? Okay, again, how many electron is present for carbon? You will say 2, because you count for this also, for this also. If I say how many electron for chlorine, again you're going to count this and this, so you'll again say 2. But if I say in total, again you're going to say 2, not 4, right? Understood this? Okay, so the total electron here is present 2, but if I ask you how many electron present in the carbon, again 2. How many electron is present in the orbital of chlorine, again 2. So understand these 4 points. First point was every bonding molecular orbital also have anti-bonding molecular orbital, which is placed opposite to bonding molecular orbital. That was second point. Third was generally anti-bonding molecular orbital are empty. Okay, and both bonding molecular orbital and anti-bonding molecular orbital can hold maximum of 2 electrons, right? Now I was going to make you how the electron can be assumed in a wave. I'm just trying to explain you in giving one example. Okay, assume it, I have one vessel, right, and I put one electron in that. Okay, suppose this is electron in a vessel and I close the vessel, right? So if I ask you how much electron is present, you're going to say 1 electron, right? Now just assume it, suppose I heat, right, I heat this vessel and assume that this particle which is there, when I heat this, it changes into a fume like substance, right? So if it a fume, let's understand in this way, it becomes smoke, right? So this, it will convert into smoke. Assume it will convert into smoke. So if this convert into smoke, then this is going to spread all over, right? So I will say this is an electronic wave of 1 electron. Similarly, if I take one more electron and if that also get convert into smoke, so it will become more denser, right? So how many electronic waves are present? Obviously 2 electronic waves are present, so it will be more denser. Now assume if I take these 2 electrons in a big vessel, right, here also 2 electron, right, but here the density, or when this electron will convert into vapors or smoke, the density will be comparatively less, because what I did, I transfer this same waves or smoke into bigger vessel. So when I did this, what will happen? The density will reduce. Why? Because density is mass upon volume. I increase the volume, so density is going to decrease. I hope you're getting that. So when I say electronic waves, you have to assume in a form of smoke or assume in the form of waves, right? So that will make the things very simple, student. Clear? Understood? Okay. Now let's start with SN2 mechanism. And this is a very important SN2. SN1 and SN2 is the most important part of the organic chemistry in the textbook. Okay, so let's understand. What you understand by S? S means substitution, right? What do you understand by N? N means nucleophile. And what is 2? This is bimolecular. What is bimolecular? It is the order of a reaction. It is what? Order of a reaction. Why it is called substitution, why nucleophile, why bimolecular, we'll understand everything. Okay. Let's start with a reaction. And reaction, suppose I have CH3Cl. Okay, this is chloromethane, or we call as methyl chloride. This chloromethane, suppose I treat this with KOH or NOH. KOH. Okay, now what the reaction will take place? This OH is going to replace this Cl, right? And the product obtained will be CH3OH plus KCl, right? This is the reaction. This is what? The reaction. Reaction is very simple. But now in this reaction, we have to understand everything in the form of mechanism. Okay, let's see. Carbon. I write this carbon. Okay, now this carbon is having 4 bonds. One here, hydrogen, second hydrogen, third hydrogen, and here with chlorine. And this carbon and chlorine I draw in orbital form, right? Suppose this is hybrid orbital of carbon, and here there's a chlorine. Understood that? And here these are electronic waves which is present. They are sharing. Okay, this is methyl chloride, and we do understand this is tetrahedron structure. So if it is tetrahedron structure, so this hydrogen and this bond of carbon chlorine, okay, this will be present in different plane. Okay, so we do understand that way. Okay, now understand, student, when this is a condition, we put KOH in water aqueous, what will happen? It will become K plus and OH minus, right? K plus is not going to do anything because its octet is complete, it is stable, it is not going to do anything, student. Okay, so this substrate which we have put, what is the function of this substrate? Substrate performs the reaction. Okay, this substrate is going to perform some reaction, is going to make the life miserable for this methyl chloride. As a result, they will react. Now understand this OH minus. Okay, now I can take other also, but here I'm taking this OH minus. This OH minus is wants to get rid of this electron. Okay, see this negative charge in what? Is present in oxygen, and this oxygen it's not making it stable. This electron is not making it stable, so he wants to get rid of that electron. So how he can get rid of that electron? He is going to come, right, and is going to give its electron to carbon. And now here actually we understand the mechanism. Let's see. See, this is bonding orbital, right? Obviously here there will be presence of antibonding orbital, right? Carbon has electronic waves which is equivalent to electron. Chlorine also have electronic waves which is equivalent to 2 electron, right? Now when this OH minus obviously is going to come from here. Okay, this OH minus will come from here right, will come close. It can't come from here because here chlorine is present and there will be repulsion between them, right? So this OH minus will come from backside. Okay, now understand one thing, student. Carbon and chlorine. Chlorine is more electronegative. Since chlorine is more electronegative, it will tend to pull the electron to itself, right? So when this electron moves towards chlorine, okay, so here there will be partially positive and partially negative. Now understand this. See, assume it like this. When I say pulling of electron, okay, assume it like this. Because chlorine is more electronegative, so electron density will be more shifted towards chlorine. Means you can assume that electron, which is actually the density should be equal in both the orbital. Because when I take a smoke in a vessel, then the density should be equal everywhere. But here, what did chlorine does? Chlorine pulled the electron from carbon. As a result, the density here will increase and here will decrease. That means carbon has less electron because its own electron is taken by chlorine. Assume this. There's a 10% deficiency. Assume there's a 10% deficiency of electron in the orbital of carbon. Assume it like that. Okay, so what this OH is going to do? See, this electron is also in the orbital. I'm not drawing the orbital diagram over here, but you have to understand when I say electron, the electron is always present in the orbital. So what will happen? This OH is going to put its electron in the orbital of antibonding orbital of this carbon. Now you'll ask me, so how many electrons? How much electron? This electron will obviously equivalent to 10% only, because what I said, that bonding orbital, antibonding orbital, maximum of 2 electrons, right? If some of the electrons shift here, then this antibonding can take some electron, right? So this 10% electron comes over here and this electron 10% which is gone. So this carbon is now satisfied because it has equivalent to 2 electron. But as soon as this chlorine solves that, this carbon got electron and now it has again become electron rich, it will pull some more electron. Suppose assume it pull 20% electron now. So this is going to put 20% electron. Similarly, what will happen? Slowly and slowly, actually 1 electron is present in the carbon, right? And 1 electron is present. If this carbon will give its 1 electronic waves into this, that means here the bond is broken, right? So if it happens like this, here OH is also going to give 1 electronic waves to this. So it will have 1 electronic waves, it will have 1 electronic waves, they will form a bond, and here obviously the bond is broken, right? Because if all the electrons goes in the orbital of chlorine, it becomes completely empty. Understand, student? It becomes completely empty because all the electron has gone from here. So, but you'll say, sir, then the electron becomes 0. No, because we are getting the electron from here. If I'm getting 1 electron from here, I can give 1 electron to the chlorine. And what will happen? This bond will break and the bond will be formed between this carbon and OH. So this will become now bonding orbital, and now this is going to become anti-bonding molecular orbital. Right. So this is how the product will be formed. This carbon, right? OH will obviously come here, and this H will be like this. I hope this is clear, right? So actually this is what happens. OH minus come from backside, it it gives an electron in the antibonding orbital. Here the electron shift from orbital of carbon to chlorine, bond gets break up, but a new bond is formed because now 1 electron, see 2 electron was there. OH, see when I say minus means 2 electron. Okay, so 1 electron he gives to carbon, he become neutral, he has 1 electron, again this share, right? So the bond is formed between them. Got that, student? Okay, this is actually what happened in SN2 mechanism, right? And this Cl minus which comes out, now its octet is complete, it's stable, so it is happy, his life is happy, right? Got that, student? Okay. Now, so you understand substitution has taken place. What happens? Substitution. OH comes in, this goes out, that's by substitution. And why nucleophilic? Because nucleophile, this is nucleo. You understand what is nucleophile? I hope you understand that. Nucleophile means nucleus loving. OH is minus, negative charge. Negative likes positive. Nucleophile, nucleus loving. When I say nucleus loving, that means they require positivity. So this OH minus is going to attack, so that's why nucleophile. Now we have to understand why it is bimolecular. Okay, actually, student, this reaction, this step which is taking place, it's a slow step. Why slow step? The reason, understand, OH minus moves from here, comes over here. See, when I say moves from here, you have to assume that they both are present in some solvent, right? They're not present in the air, they have some solvent. So there's a medium. So this OH minus have to float to that solvent, have to come on the back side of this, okay? And then slowly and slowly, this is going to put the electron. It is not going to put its electron, 100% electron in this orbital. It's not possible, student. Because if all the electron comes in the orbital, this electron and this electron will be more than 2 electrons, which is going to make them highly unstable. And this carbon is not going to do that. Right? So it will take some electron. How much? The amount which is required will take that much. Suppose 10% comes here, 10% moves out. Again 10% comes here, 10% moves out. So this takes time. Right? It requires time. It's a slow step. It's not instant. Right? It requires some time. That's why this is a slow step. And there's one chapter in 12th, obviously you'll be studying that, and it's paper 1, that is called as chemical kinetics. Chemical kinetics talks about the rate of reaction. So here the rate of reaction depends upon two things. One is nucleophile, another is methyl chloride. So when I say rate of reaction, speed of a reaction, because two things are involved, student. In this slow step, OH is also required and CH3C is also required. So this rate of reaction is directly proportional to the concentration of CH3Cl as well as the concentration of nucleophile, that is OH minus. Right. So this rate of reaction depends upon both. That's why it is called SN2 mechanism, because 2. Right. So its order is 2 because in the slower step these two are present. Right. Clear? Okay. Now, so I hope you understood what is SN2 mechanism, and if you remember all the reaction which we have done earlier, I think all the chemical reaction we have done, in that I have explained the same way. It goes from backside, attract. I have explained that, but actually this is a mechanism, right? And there are certain factors on which this depends. Obviously, that will be dealing in the next lecture. Okay, but for time being, for today's lecture, we'll stop over here. Next lecture, we'll see what are the factors on which this SN2 mechanism depends. Right, and then we'll solve some problem which will be based on this reaction. Okay, so today we stop, student. Thanks for watching.